missing some folks today, but Michael's, oh, I won't say Michael's always late on video. We love you, Michael. All right. All right, let's just take a minute. Close your eyes, settle in. We'll do something very simple but profound today. Just explore the boundary of your body. Look for it with your eyes closed, not using preconceptions of where that boundary is. If you've never seen your body, where would you guess the edge is? That becomes too overwhelming, just go to a hand. Discern the shape of a hand. Although we could keep doing that for a long time, it's somewhat soothing. Let's just come back. Take Kayla's questions and any others. I firmly believe mirrors are tools of the devil. I really believe in the devil. But I think mirrors really have fucked us up in who we think we are. I think they're the cause of a lot of suffering in this world.
That's fair.
Yeah, right? You like look at that, you like see this thing that looks like it's separate from everything else. See a little boundary, looks like a boundary around it. Then identify with that, identify with all the things people are reflecting back on you about your body and have since you were born. Can't help it, gonna be reflections in the world, but yeah, I'm not a big fan of mirrors. Probably clearly. That's what my wife would say anyway. So, yeah, yesterday I was like, I had this look going and I was like, you know what? I think I've perfected my professor look. I like it. I got the hair. It's a matter of not, now I take showers, I clean myself, I'm not a filthy person, but not like washing my hair every day. I used to wash my hair every day. Now it's like twice a week.
Huh. It's better for your hair.
Yeah, it is. Yeah, it's good
So
for your
much
hair.
better for your
And it's good for your professorness. All right, I got a pen here. Kayla, my friend, what can I do for you?
Okay, so for 264A, I don't know if this counts,
Okey doke.
but like I can, just because, okay.
Oh, right, yes.
So-
Yes.
If I let a sub n equal 2 over n, and then C sub n is 1 over n, which is Cauchy. C or no?
Okay, so C.
Okay.
C. But we can come up with a more general argument, and let's maybe think about how we could do that. Let's see here. I think we can. It's definitely true. And here's like the intuitive argument as to why it's true. This absolute value action here can really only bring things closer together. Because you think the furthest things can be apart from each other would be to be opposite signs, right? So once you do absolute value, that brings things closer together, puts them on the same side. Wait, no, that's different. No, I'm thinking of something different. I'm thinking taking the absolute value of each one and then the difference. So that's literally not true. What do they ask you to do here? Just justify, justify
It's
each.
Cauchy or not.
Yeah. Okay. Yeah, I thought for a minute I was thinking the order limit theorems were probably the way to go, but not necessarily. And those things are going to switch sign. Noah, did you come up with one for this? No. Yeah. Okay. Okay, cool. It's good. It's good we have the homework. Diana, you got anything on it?
What's this one?
This is 264A. Why is that so?
Could you make an argument based off boundedness? So if we know that A sub n is Cauchy and B sub n is Cauchy, then
so I'm sorry, I didn't mean to cut you off.
no, you're good.
So one thing to keep in mind is the Cauchy criterion.
Yeah.
Because like we've got this new idea of Cauchiness, and it's like, whoa, it's this whole definition. But just remember, that's the same thing as convergence.
Yeah.
So here we literally can just say A sub n is convergent, B sub n is convergent because they are Cauchy by the Cauchy criterion, and you would want to say that.
Yeah.
Can we just then use the thing where it's like we know what the limit goes to with two convergent sequences?
Oh, yeah.
Yeah,
would
I think
use the
that
limit
sounds
theorem.
completely reasonable.
Or the algebraic limit.
Yeah.
Yeah, that one.
Yes.
Okay, cool.
Yeah, I think the ALT is the way to go on that. I will definitely think about it and see if there's a subtler answer. I think that sounds completely reasonable, though. Any other questions? Because that's really the way to do that whole question, right? C sub n, no, yeah, I think you're good to go. I think just thinking about convergence being equivalent to Cauchiness is the right way to go. Did I assign part C?
Yes.
Oh, of course I did. Of course I did. So we've seen some examples. We actually did one like part C. If you haven't gotten to part C yet, there was actually a problem maybe on the last homework set. There was one where we were using the ceiling, and we had to come up with an example of a sequence that converged but did not converge when we did that ceiling function. Do you remember that one? What problem was it? I don't know. I can't remember that. I know we had something like that in a problem. And it's basically the same problem, just with the word Cauchy added in.
Oh yeah.
Right?
I think I do remember it. 'Cause
Yeah.
we got it by doing like the 0, 1,
Yeah.
1.
Yeah, exactly. Yeah. And the key on that one was if a sub n changes sign, then rounding it up is going to do some different things to the positives versus the negative terms in the sequence. So that's my tip on that one. Think about an alternating sequence that converges. That's the way to go. Other things to discuss here. Yeah, Trinity, yeah.
It's 2.5.2.
252. Okay. Yes.
C.
Ooh, okay. 252C. So here, decide if it's true or false, briefly justify. We have x sub n is bounded and diverges. Then this implies that there exists two subsequences and that converge to different levels.
So like this one, I like it. It makes sense that it would be true, and like using the Bolzano-Weierstrass theorem and putting that in, whatever. Like it intuitively makes sense that it should be able to have two that converge to different values, but I don't know how to like actually.
To get the justification, the like solid justification. Okay, cool. So Bolzano-Weierstrass, definitely something we have to appeal to here. So from the boundedness, we know that from Bolzano-Weierstrass that there exists a convergent subsequence. That. Now, then we bring in this piece of information. So if the sequence converged, what would I know about it? We have another result. So let's just say if x sub n converges, in fact this is maybe an if and only if. Let's say this, if and only if we have a result in that section. Maybe it's in the next section. Yeah, it's actually in, no, maybe it should be in that section, or maybe it was a problem. No, check out Theorem 252.
Yeah.
Yeah, that's the way to go. So subsequences of a convergent sequence converge to the same limit as the original sequence. So we have x sub n converges, implies, I'm pretty sure this is an if and only if, converges if and only if, or how about we say to L, if and only if every subsequence converges to L. That might have actually been a problem, maybe not. Every subsequence, x sub n is okay, converges to L. So that's a really nice way to put that result out. So if we have divergence, then we have to have, and we have to have another subsequence here that would converge to a different limit. Because if this didn't happen, if all subsequences converged to the same limit, this result would tell us that the sequence converges.
Yeah.
And so that would contradict the hypothesis.
Okay.
Does that make some sense?
Yeah.
So I think that the trick here will be to get that, get that gelled in your head.
Yeah.
But that you're on the right track if this is what you're thinking.
Yeah. Okay.
Yeah. And the fact that there's a small amount of suffering is good. That's good. Good math suffering. Other things to discuss in this assignment. And then I realized, so I'm not going to be on campus on Friday. So if you want to turn your assignment in on Monday, that's just fine. Is that okay to everybody? Because why force you to get it in on Friday when I'm not going to pick it up till Monday morning? So that's great. But I am going to make a new assignment. So I will release a new assignment to motivate you to get done. Alrighty, my friends. So we are closed sets. So let's do little karma-free quiz. On your own, just to strengthen your mathematical knowledge and real analysis skills. What is the definition of an open set? Yeah, you can think you don't have to write it, but you know, be aware of what that is. And then what is the definition of a closed set? Maybe you don't know the precise definition we gave the other day, but if you understand the intuitive idea, then that's good enough, really. Trinity, you got a definition for me, friend?
Kind of clunky.
That's cool, clunky. Who gives a shit? Let's get that out.
But there's, so it's open if there's some neighborhood around each point in the set that's fully contained in the set.
Yes. Yeah, absolutely. Yeah, there was no clunkiness in that. You actually just had the quantifiers in a slightly different order. So, let's actually talk about Trinity's definition, because sometimes, like, if you can remember something correctly in your own language, that's more powerful than memorizing a definition. So, if there exists a V epsilon around X for all, and then that's where the for all, and I had it presented in the other direction, it's all good, for all, contained inside A for all X in A. Beautiful, nice, thank you. That means that no matter, and I'm gonna draw this in 2D even though we don't have 2D, but you have some set, because this idea transfers to all dimensions. It's the same even if you have infinite dimensions. Openness is the same. You take a point in there, no matter what point it is, I need to be able to find some open neighborhood around that point that's contained in the set. If I have things like a boundary on the set, then that kind of messes it up. So that point right there, no open neighborhood is completely contained in the set. If I have that's literally how you define a boundary. A boundary of a set is the collection of all points where some is in the set, some is not in the set, for every open neighborhood around that point. How about closed? Diana, you got one for me? No? Okay, that's cool. No.
If it contains all its limit points.
Beautiful. If A contains X. What's a limit point?
A point which a possible subsequence of the set could converge to.
Oh, nice. Okay, you've been reading. That's good. That's excellent. Yeah, so Noah just invoked a nice result, Theorem 325, and let's just talk about it really quick. So the way we originally defined limit point, a limit point of a set A is any point x where v epsilon x intersect A is non-empty for all positive epsilon. Should have put that up there. That's a limit point down there that I drew. That both those are limit points, in fact, that I've drawn up there on that picture. Even though it's 2D, same ideas. That's one of the beauties of topology, is that it speaks in these general terms that apply in infinitely many situations. So Noah actually gave us a different one. And let's actually do the proof of how this would work. Let's say I have a limit point. So we'll work back in 2D. So here's my set A, real simple, closed or open interval. We don't care what the endpoints are, but this point here, right on the cusp of that, so think open interval 0 to 1, and this is the point 1 right there, just to make it a little solid so you see what I'm talking about. If this is a limit point, then every open neighborhood around this point intersects. If we pick a very particular epsilon, so if we use epsilon equals 1 over n, then this would be x plus 1 over n, and this would be x minus 1 over n. So in other words, I've got this neighborhood that I'm looking at right there. And n is going to be a natural number. So for any n, v 1 over n of x intersects A. They have something in common. So what I do is, for each n, choose some element out of this set, this intersection. Choose x of n in v 1 over n x intersect A. Choose one of those things that they share in common. And in doing so, what I do is I construct, I construct a sequence of points that are getting closer and closer to that limit point. So this produces a sequence x sub n, where x sub n is converging to x. And in fact, all these are also in A. So if I can find a sequence of points in the set that converges, the thing they converge to has to be a limit point. And now that pulls it all back to the idea of limits, of sequences. So it's a really beautiful, full roundabout. And that is an if and only if. We're not going to prove the other direction. You can read it right there. But we say a limit point of a set where, or if there exists a sequence x sub n completely contained in A such that x sub n converges to x. That makes the limit part stronger, the idea of the limit. Stronger. Beautiful, thank you, friends. Let's go back, let's talk about openness for a minute. We're gonna explore this. Is it okay if I erase here? Pretty much our first theorem. Well, Noah actually just gave us our first theorem out of this. Now, bye, Noah. He's out. He's done his work. He's gone. He doesn't need to do any more today. I want to look at theorem. Theorem 323, very important theorem. And talk about the proof. Theorem 323 is all about open sets and how they combine to produce new open sets. So the first part is arbitrary, we're going to get some new notation, which is going to be really cool. Arbitrary unions of open sets are open. Let's just start there and then come back on this. So this is arbitrary unions, and I want to introduce maybe something you haven't seen or you saw in Logic and Proof for like a brief flash. Depends on who taught that. Who'd y'all have Logic and Proof from? Duval? Okay, cool. So she probably hit this if it was in the book, because she hit this because she's very meticulous about that stuff. So, proof. Let O's, so check out, so open sets are commonly notated with this kind of script O. Let O sub lambda, where lambda is an element of an index set, be a collection of open sets. I'm going to explain that in just a second. Be a collection of open sets. This notation is really wonderfully general because this index set here could be finite, this could be countable, or it could be uncountable. So make a little note here. Note, lambda is an index set, which can be finite, countable, or uncountable. Big deal, actually. I put an exclamation point, I guess, I got excited. So, e.g., could have something like this. I could have a finite collection. It's finite. I could have a countable collection, which would then be, or we could have this. Oh shit, sorry, take these out. So, and then that goes up to n. Here, my index set, lambda, would be 1 through n. So I'm just grabbing elements from that set. It could also be like this. Dot, 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 implying that lambda is equal to the naturals. Or it could be wild, and we can't write it any other way like this. Here we might have an open set associated with every real number. Notice here too, that lambda, or we could have had this, maybe something like this. Lambda could have just been Q as well. I associate an open set with every single rational number in the line. That sounds pretty crazy, but it's no different than this, we know that. So we've got an arbitrary collection, and if we union them up, we still have an open set. Let's just quickly go through that proof of this. Given a collection of open sets, let's talk through the proof together. If you fill in the blanks for us, consider the union. Now watch this. I don't know what that index set is, so I just union like this, saying grab lambda from the index set. How do I show that's open? How do I show that union is open? Ooh, great bathroom break for me. I can see it. Small pause. Prove that's open. Without looking at your book or remembering maybe what you read. prove stuff's open. I mean, what's the definition of open?
At the neighborhoods.
Yeah. Yes. That's, yep. That. So we're done. Proof.
Yeah.
QED. So, what do I have to show something's open? That every point in that set has an open neighborhood contained in the set. Or has an open neighborhood contained in the set. So we're gonna take X in the union. Now remember, I only know that each individual element is open. So I've got to pull back to the things that I know. What does having X in this union mean about X? What's the only way you can be in that union?
It's in some set.
It's in one of them, right? So this implies X is an element of some O sub lambda, let's call it not to fix it, for some lambda not in the index set. And so you've got to get used to this new way of thinking about grabbing things and indexing them, but it's, just a little bit of practice. So if X is in this, what do I know? This means what? Let me help. Let me pull back even more. Because O sub lambda naught is open. What does that mean? Don't think too deeply. It's literally, we're just almost saying the definition like over and over again.
That there exists an epsilon neighborhood around X that,
Yeah, exactly, perfect, yeah. This means there exists some V epsilon of X completely contained in O lambda naught. Epsilon is positive. Why are we done? Pretty much with sides thus. What did I want to show that neighborhood is in? What am I trying to show is open? Yes, the beautiful. So if you're in one of the elements of the set, you are also in the union by the definition of union. Done. We took a point in the union, constructed a neighborhood around that point because it lives in an open set. Therefore, that open set is also contained in the union of all of the sets. So good. The next one's a little more subtle. So Theorem 323, part 2. And this will be an interesting discussion. We'll learn something good here, or pull some things together. Part 2 is about intersections. The language here is very different. If O sub lambda 1, O sub lambda, so wait, is that the notation? Let me just make sure I'm using the right notation here. Oh, no, they have a much more beautiful statement of it. That's just clunky. The intersection of a finite collection of open sets is open. Big difference. Totally arbitrary. Arbitrary is okay for unions. Now we have to restrict to finite, and that's the discussion we're going to have. Why is that the case? Let's go through the proof. So, let O sub, again, why do I don't need their notation. I can come up with notation. I'm a big boy. O2 be a finite collection of open sets. Take a point in their intersection. does that mean about X?
It must be in all of them.
Yeah, nice. Yeah, exactly. So then X is an element of O sub I for each I equals 1 to n. Very nice, Kayla. And then, any ideas on where we go next? We haven't used something yet that we clearly will need to use. Some property of the hypothesis.
It has a V neighborhood around it in all of them.
Exactly. So, and since O sub I is open, for each I equals 1 to n, there exists V sub epsilon sub I. I don't know what epsilon's going to be for each of them, but I know it exists around X contained in O sub I. So for each of those neighborhoods. So let's take a look. Let's look in 2D. Sometimes the 2D pictures are a little more helpful with thinking about this. So let's say we got open 1, open 2, open 3. Unless 3 will be enough. It's already going to get a little clunky and cluttered. I think I picked up your word clunky, Trinity, and now it's like stuck in my brain. So I'm picking an X in the intersection. And then I'm going to pick an open, let me pick it a little closer to the edge of one of them, just to make a point. So there's the X in the intersection, and I'm going to pick, so let's call this is O1, this is O2, and this is O3. So in O2, I have to pick a tiny neighborhood. So that's going to be radius epsilon 2. And then I pick an epsilon so that it's an O1, and I can go a little bigger there. Right? Okay, I'm going to make the open sets with a solid boundary, even though we know that's not what they actually are. So then this would be epsilon 1. And then finally we've got an O3, so we've got epsilon 3. I got to make sure it's in there. So it could be pretty big. Epsilon 3. That may or may not be helpful now that I step back and look at it. But what could we do to find one open neighborhood that's in all of the open neighborhoods?
Find the min of the epsilons.
Perfect. We'll just pick the one with the smallest radius. Yeah? So let epsilon, our final epsilon, equal the min of epsilon 1 through epsilon n. So that V epsilon of x, this now has to be contained in every single other neighborhood because it's a small epsilon centered at x. They're all just balls, or for us, little open intervals, is contained in O sub I for each I. Hence, V epsilon of x is contained in the intersection of all of those. And we've now produced our open neighborhood in the intersection. Hence, and by the definition of open, we are done. We have produced an open neighborhood in the intersection. now it gets a little deeper. Let me get you let you get caught up. But we've got kind of a deeper question about this proof. It all looks fine. I mean, it is fine. Why is finitude important?
So that you can take the minimum?
Yeah, definitely. So that's absolutely right. I can't take the minimum of an infinite collection and hope and expect that it exists. It might, but it doesn't necessarily have to. What would we have to use if we had an infinite collection? Not min, but what? Not max. No. Max and min are very fine. There are things better for finite things, or things you know will actually attain certain values. So if we had max, what's the infinite? So these are finite kind of things, and then here's infinite versions. What's the infinite correspondence for max? Gotta see which points. Doing that. Can't quite get there, but geez, it sure looks like they're approaching 1.
Limits?
Limit, yeah, definitely related to limits, but what are our measurements in real analysis for like biggest and smallest, but not exactly? Soup. Yeah. So if you're not sure that a value is attained, then you need to work with soup. If you know a value is attained, then you can work with max. So whenever you're in finite situations, max and soup are identical. And so inf is the thing I was thinking about for minimum things, right? So if I had something like this, I don't have a minimum, but I sure have an inf of 0 for that one. So we would have to go to inf. Can we think of an example of an infinite collection of open sets for which there is no open set in their intersection? So produce an infinite collection. And let's just say countable. We don't have to get too crazy about all this. An infinite collection O sub n, for which there is no open set in the intersection. And you have done this. In fact, you did this a long time ago, when the world was young. You got one, you think?
Maybe I don't have an example, but I think I know what property you're talking about.
Yeah, so like explain what your feeling is about it anyway.
It's like when we were talking about the nested interval property. So like if you just continue to take the intersection, then eventually nothing will be there. Or be in the intersection.
Oh, that's a good, yeah, that's pretty cool. I hadn't even thought that direction, but that's great. So we could do, I think Kayla is referring to like this. So O sub n equals n to infinity. That's great. I hadn't thought about that, but yeah. So we've got these open sets that look like this. They start at n, and that n is slipping that way. And of course, the other end of the openness is way out at infinity. There's nothing in that intersection.
Would that be the empty set then though?
Yes.
Cause then the empty set
Oh
is
shit,
open.
that's good. Oh no, it is open.
Yeah.
That's right. Good call. Good call. but awesome thinking, right thinking, absolutely right thinking. But that's, yeah, thank you, Trinity, solid. This actually is not an example, but that's the right way to think about this, Kayla. So your intuition is good, for sure. How can we get something in the intersection, but there's no space around that thing?
Do like 0 to 1 over n.
Like this? Yeah, is that what you're saying? What's the intersection of all these? That might be the same problem we have up here.
Never mind. 1 over, negative 1 over n.
That's it.
1 over n.
That is an example. It's empty. Oops, open. Again, so yeah, that's the intersection I'm thinking of, Noah. And what's in the intersection?
No,
Hmm?
0.
0.
Yeah.
Yeah, and that's it. There's no space. Literally just that single point is in the intersection. Good thinking. Really nice. All right, let's look at some closed set stuff for just a little bit. Let me let you get caught up. Oh, yeah, a slightly different definition too. So while you're getting there, I'm going to create a set here. So I want to ask you some questions. Those are the questions. I would definitely draw out such things, right? At least to the best of our ability. Any thoughts? Kayla?
Neither.
Not like a door at all, right? How do we feel about that? Neither open nor closed. Does it feel right? Yeah? cool, absolutely. Nope. Nope. So, open, take an x, an a, that implies x is equal to 1 over n, and if this was open, there would exist some neighborhood that's in there, but we can clearly see, and we could prove this a little more rigorously, that at 1 over n, let's see, what do we got here? This is 1 over n minus 1, and then there's 1 over n plus 1, then all I have to do is pick some epsilon, reasonably small, and it will fall between points, and it won't touch. It will not, certainly not be contained within the set. This is just a bunch of points. It's going to be hard. Openness is like there's stuff. There's substance to the set. It's got a filling. There's no filling here, so yeah. So no v epsilon of x contained in A for any epsilon. For any x. And then closed. Why not closed, Kayla?
Well, okay, we can see that 1 is a limit point and it's closed, so that's good, but 0 will never be reached, and 0 is a limit point, and to be closed you have to have all your limit points.
That's quite beautiful.
Wait,
Yes,
is
indeed.
one a limit point?
Yeah, that's, so the
Because-
first part, that's not, yeah, it's not actually a limit point. To be a limit point, what was the thing you
Ooh,
said,
sorry,
Noah,
yeah.
at the beginning of the class?
It has to be able to converge to 1.
Yeah, there has to be a sequence in the set converging to it. So to be a limit point means, and there's another great word for it. Limit point is the same as accumulation point, which is actually a little bit more suggestive in that things are building up around it. Sometimes even called a cluster point, where the points in the set are clustering around a locale, and then that's the limit point. So, yep, exactly. But you are absolutely correct that 0 is a limit point, but not in the set. So it can't be closed. Let's stick here for a minute. So what are these points? So what is 1? Does anybody know from the reading what we would call those points? There's a special word for them. We gotta have labels for everything, right? We're humans.
Isolated points?
Indeed. That's a great term, right? Because it's literally suggestive. They are isolated. They have space between them and other elements of the set. So, all points in A, no matter where, are isolated points. And what this means is, i.e., for each point in A, there exists an epsilon neighborhood around that point that doesn't touch the set at all anywhere else. So we could even say punctured neighborhood to just disabuse ourselves of the notion that the center of that point counts. For each x in A, there exists a punctured neighborhood that does not intersect A. Epsilon positive. So no matter how deep you get, even though they're clustering, right, you just need a microscope and you zoom in and you blow it up, and eventually it all looks just like this picture, no matter where you're at. Even if I pick x is 1 over a Google, here's x, here's 1 over a Google. Well, Google's a big ass number, but it's still bigger than a Google minus 1. Oh, smaller than a Google minus 1 and bigger than a Google plus 1. I haven't said Google in a long time. Not in a good way. not in the pure math way. Yeah, very nice, very nice. So let's more stuff here. How could I make A closed? what could I do to make A a closed set? Besides, like the simplest thing I can do. What's the smallest move we can make? Smallest move. The fewest things we can include into A to make it closed. Yeah, exactly. So notice if I take the set A and I toss in this trouble spot that's not in the original set, but if I union in 0, now this is a closed set. So note, A union 0 is closed. And in fact, this is a special term. What we've done is we've created the closure of A. A union 0 is the closure of A. So the closure of A, and for any set in subset of the reals, closure of A, there's all sorts of different notations for that. We're not going to use it enough to worry about establishing a closure or a closure notation. Closure of A equals A union the limit points of A. You take the things that are keeping it from being closed. The limit points aren't in the set, and you toss them in. We have another theorem here. This is also equal to, and this is why I was saying the fewest things to kind of hint at this. This is the smallest closed set containing A. It's the least you can add to the set and have it be a closed thing. You could, of course, add lots of other stuff and make it closed. You could add all the reals, and there you go.
So we're considering A as a set and not a sequence.
So after this, so this is still for the example here, and then this is in general. Here, Noah, so that could be any set in the reals at that point. Does that clear it up, or?
Well, it was just about, like, if A is still a sequence, where does 0, is it just at the beginning now, or
I think.
do we not care, or do we just denote it as that?
So this, I'm pulling away from that original example of the sequence over here.
Okay.
And I'm just saying that no matter what the set A is in the reals, to create its closure, I add the limit point. So let me add an example here. Let A equal, let's do some, okay, I see what's gonna happen here. So let's let A equal 0 to 1, union 1 to 2, union the point 3. So draw that set out. So 0 to 1 to 2, and then we just toss in the point 3. Is that set open? Why not, Kayla?
Because it's not full between 2 and 3.
Yeah, because 3 is an isolated point here. Yeah, exactly. So if 3 wasn't in there, then it would be open. But we tossed in that 3 and it kind of mucked things up. So this is not open. Is it closed? It is not. What can I do to close it? Toss in what points?
0. Yeah.
Fill the holes, right? So A is neither open nor closed, but the closure of A equals A union its limit points 0, 1, 2, and that's just now this set here. That is a closed set. there is a companion. I don't know if they mention it in the book or not, but there, to get an open set from any arbitrary set, you can create the interior of the set. So similarly, we can construct the interior of any real set A. What do you think, how do we think we do that? Think in terms of some ways, what do you think the interior is? And this will be an open set. This might be too weird a question, because you kind of maybe don't know where I'm thinking. What would be the companion? Go ahead, no, yeah.
So if it's like 0 to 2,
Yes.
the interior of that's already there.
Yes.
And so I don't know how we would construct the interior.
Yeah, yes, yeah, that's, yeah, fair enough, yeah. So in the same way that the closure is the smallest closed set containing the set, the interior, we work from the inside, and we find the largest open set contained in the set. So the interior of A is equal to the largest open set in A.
So then of 0 to 2, wouldn't that just be like the open set of 0 to 2? Does that make sense? Removing
Yeah, but we still have to keep out 1, right? So we don't want to toss in, with the interiors, we're not going to add things in. We're only going to work with what we have. So for this one here, this stuff's on the interior, this stuff is, that is not. So for this set over here, thinking back to our example back there, the interior of that A is just 0 to 1 union 1 to 2. Again, think openness is fullness, stuffness. Here's a question for you. Consider Q. Good old Q. What is the closure of Q? What is the interior of Q? Ooh. Do you think you got some ideas now?
Yeah. It's just these two.
Yeah.
Wait, so
Yeah.
back to yesterday for that error Monday for the sequence thing. How can we have an infinite
You need more
where we
details.
could have the third in the middle?
Oh, yes, yes.
So there has to be more than rational numbers in it, right?
Correct.
So it's not just the limit points at the end, even though it seems like it.
Yeah, because it's really interesting. It's actually a closed set, because it's literally the intersection of closed sets. We haven't taken a look at that yet, but arbitrary intersections of closed sets.
I was just thinking about it, and I realized, wait, there's a lot of things I saw.
Yeah, no, that set is baffling. Yeah.
Yeah, because shouldn't all the interior points, shouldn't all the end points be rational, and therefore we have the same amount, a subset of rational numbers between 0 and 1 that are represented by the real numbers?
Yes.
But they're not countable.
I know. Yeah, you're right. That's a really good observation. There has to be something in there. that is not rational.
I don't know, I'm gonna stop thinking about it.
No, that's good. No, it's good. That pain is so good. That's what we're in this for, right? I'm pretty sure I've told this story before, but when I was in grad school, I was like so neurotic. Like grad school, I'm not discouraging you from grad school, but it destroys your mind and like and your soul. It's a hell of a gauntlet. Like I was just like, when I was at Purdue, I just became so neurotic, and I didn't really have that many friends there. And I stayed in my little room and like obsessed over, am I losing hair? I remember looking, am I losing hair? Am I losing hair? And this is like, I mean, my hair's thin, but you know, still got something up here. But I was like just freaking out about that. And to go to sleep at night, I would count points on the infinite dimensional sphere. Like sheep. And after we talk, so next Monday we're going to talk about a thing called compactness, and the infinite dimensional sphere is not compact, and that will make sense to you. That will literally make sense to you at some point here, maybe Monday. But yeah, it was just like, I don't know, it just felt really good. This is very soothing. It hurt. It was like, I can't do it, but I'm going to try, damn it. Let me just 2 more results. I know you're packed. You got to go. We got 5 more minutes. Oh, wait. How about answering the question? What's the closure of Q? Ah. I know it's got it. R.
Yeah, so it's the union
Beautiful.
with I.
Yeah. So think about how every real number can be approximated with a sequence of rational numbers. So in the rationals, we can always find a sequence in the rationals converging to any real number we want. You want square root of 2? That's in the closure, because we can find a sequence converging to it. 1, 1.4, 1.41, on down the ways. What is inside Q? What do we think's inside Q? Oh, here's Q. All right, here's 1/2. What neighborhood can I find that is completely contained inside Q? None. Because no matter what point I pick here, so if I go 1/2 plus epsilon, 1/2 minus epsilon, are there irrationals in there? Yes, there are. If you don't believe me, and you might not, just think about 1/2 plus square root of 2 over n. You could shrink that down. That's a hell of an irrational number. You can get inside any little neighborhood you want there. So there's nothing inside of Q either. Again, neither open nor closed. Last result, I just want to say really quick, we have this theorem that relates open and closed sets, and this is theorem 3213. And it says basically this lovely result that's good to know and helpful sometimes. A set O is open if and only if its complement is closed. That can get you a lot. And in particular, it can get you a result that maybe you weren't buying the other day, that the empty set is open and closed. Because we know, so let's just do an application of this and then call it a day. The application is show empty set is open. Well, since the reals, the set of all reals is closed because every sequence in there converges in the set, our complement is equal to the empty set, must be open. Or, yep, is open, and then vice versa. Can you see the companion on this? Yeah, that this is closed because the reals are open. All right, thanks everybody. Stay toasty in the next couple days. Keep an eye on your email. There's another winter storm coming in for Monday.
Okay.
Okay, so mostly you, I don't want you walking here. But I think I have your phone
Yeah,
number.
you do.
So I will absolutely text you directly. And again, if you want a direct text,
I'm not,
send me that
checking
info.
my email.
What's that?
I do not check my email before I come to this class.
Okay, then I will